this could be a very complex non-linear function, which could be a neural network. And since we can employ a neural network to approximate the Q values, right? And the parameters of the neural network will be that W, okay? Then why not a deep neural network, right? So I hope you're getting some ideas, but yeah, as we will go through this particular session, these things will become much more clear, because it's one thing to put a deep learning or deep neural network to approximate Q functions, and it is another thing to actually train them and make them converge, because convergence is a big issue in these deep models, right? I hope if I've gone through other sessions on deep learning, you must understand that convergence is not easy, and a lot of things you have to take care of. Similarly, in reinforcement learning, there are those kind of issues that we need to deal with. Okay, so with that, let us begin. So I have this one slide only for deep learning. I'm not going to talk a lot on deep learning. I'm going to talk a lot on deep reinforcement learning. Okay, but just to put things in perspective, right? So what is deep learning? Okay, and how this deep learning is different from usual machine learning, right? So usual machine learning is the typical machine learning that people do outside of deep learning, using your support vector machines or using your decision trees, or naive-Bayes or any such method, right? So in a typical machine learning, let's say the problem is, given the image of a car, you want to find that whether there is a car in that image or not a car. So it's a proper supervised learning task. And most of the deep learning is very well suited for supervised learning tasks. Obviously, that there are success again in deep RL and unsupervised learning and all those things. But the where it started, and most of the success is attributed to supervised learning domain. Okay. So in a typical machine learning, for the same task, what are the steps involved? In a typical machine learning, what you will do, given the input image, first you will do is feature extraction, right? So you will try to find the features or extract the features from this car. Now, what could be the features? Features could be, okay, maybe how many circular patterns are there in this image, right? How many corners are there in the image? How many edges are there in the image, right? And similarly, a lot of such features could be extracted. Once the features are extracted, you input these features to a classification algorithm, which could be a neural network algorithm, which could also be any machine learning, your support vector machine algorithm, your naive-Bayes algorithm, your decision tree algorithm, your regression algorithms, any proper classification algorithm, you can give this as an input. And then we train this algorithm on this set of features, okay, with our supervised or labeled data. When this classification model is trained, then we will be able to classify any input, and we will be able to tell them whether it has a car or not a car. Now, what does deep learning do to this process? Okay, so usually in machine learning, this feature extraction is actually a very labor-intensive process, very complicated as well. Okay, we don't know that what all features is actually important for this particular classification. And even as you change the classification task from one task to another task, the set of features required or important or pertinent to that classification may change. This knowledge is usually not available, right? So then how do we extract features? And this is also called handcrafted features. Many times you combine and create features as well. We need a lot of domain expertise to do that. It's only the domain expert that can tell you that, if you want to achieve this particular task, what are the important features in that domain, right? If you want to trade in the stock market, a domain expert from the stock market can only tell you that what are the indicators that you have to, maybe it is the Sensex, or I don't know, maybe there could be a lot of other indicators, right, in the stock market that you have to keep track of in order to perform any task, right? So first problem, domain experts were required, and the domain experts are not machine learning experts, right? So machine learning experts are separate, domain experts are separate, and then domain experts knowledge is required to actually come up with these feature extractions. Or what you can do is, or what people do in machine learning, used to do in machine learning, is you deploy or employ a set of generic feature extractors, right? So you say, okay, yeah, these are some generic feature extractor, I'll extract these features and try to learn on that. Okay, and all your accuracy or all the performance of your classification is heavily dependent on the features that you extracted. So this used to be the story, and then deep learning came, and magically they transformed this pipeline. What deep learning does is, the most important aspect where deep learning actually helps in this whole machine learning task is, they combine the feature extraction and classification in like one unit. So now what you have to do, you have an input, you give this input to some deep learning model, right, which automatically extracts features, right, or maybe it attracts a lot of features, and then it's checks with the classification, obviously with backpropagation, classification error, and everything. What features are more important for this classification? What important features are less important? More important features, those weights are increased, those weights are kept better. Less important features, maybe those weights are reduced. And finally, you have a model which does features discovery by itself and also performs classification. What could be better than this? And that is the advantage that deep learning brings into any domain, right? This typical job of feature extraction is now removed, because now this deep learning model can do automatic feature discovery based on what is the task at hand, right? And so usually, the typical way of extracting features from an input image is putting CNN layers, right? So if you know about CNN layers, right, you put a set of CNN layers with the filters and you generate feature maps. The name is itself says feature maps, sometimes also called activation maps. What are those? Those are trying to extract features from that image. A lot of features gets extracted because we don't know where the important features are, right? So that's why deep learning are very deep, right? You have to create a lot of layers and extract a lot of features as well. So these, channels are, you extract like 512 feature maps, right? Some 128 feature maps or things like that, right? And the importance ones are automatically saved or kept by the deep learning model with that back propagation or learning with the gradients. Okay, and the unimportant ones are automatically, their weights are reduced. That is the quality of deep learning models or any neural networks, right? So this is the advantage that deep learning brings in. What we are going to do is, we are going to assume that we understand deep learning, or at least this input and output is clear, right? So in an input, we can give any input to deep learning model, and so the input could be your state and actions, right? The description of your state can have a lot of values, right? And even your actions can have a lot of values, right? So all those information is given as an input, and the output we are expecting now is maybe the Q value of that state. So it is like a regression task. You can imagine it's not a classification task, it's a regression task. But what features of the state and what features of the actions are important in order to predict the value, the Q value of a state, is automatically learned using a deep learning model, right? So this is how we can describe a deep Q learning model, right? So I explained you Q learning earlier in the previous session. What happens in Q learning? We have state and action. We create a table out of it, right? So for each state and action pair, we are not looking inside state and inside action, how the state looks like and how the actions look like. But whatever are the possible state and actions, we create a table out of it. Then we update the values in the table, right? And finally, the table values converges. And whenever we need a Q value, we ask this table. We take, so you can assume this Q table as a Q function, right? And we give it state and action as input. The table outputs the Q value. And here the learning happens on the values directly. In deep Q learning, if you have to implement deep Q learning, right? And we're going to discuss deep Q learning or deep Q network actually going forward. What happens is, we replace this table with a neural or a deep neural network, right? A deep model where only the state is given as an input. Now, a state could be maybe the image of the system, right? The state is whatever state descriptions, the way you have described your state in the environment, that has given as an input. And the model learns to predict the Q value of all possible actions in that state. Okay, so in here, where the learning is happening? The learning is happening with all the parameter values of this neural network. The parameters are learned in such a manner that we should it is able to predict the Q values of all possible actions. Right now, here we are saying the Q value of all possible actions. That means we are not assuming a very huge action set, and we are also not assuming continuous actions, because if you assume continuous actions, like this output is not possible, right? Because in continuity you can have infinite number of actions, right? So obviously there are other models for that. We'll not deal with that models today, but yeah, you can go and read about it definitely. Okay, so I hope you got the idea, at least a very high level idea, that how deep learning is going to help. Now we will delve into inside this particular network. We'll see that how to train the network, what are the issues in the network and those things. But high level idea, I hope, is clear. Right? Okay. So initially, like where the whole thing began, so these people at Google's DeepMind, they said that, we want to make the computers more smart. We want to make the computer like learn by itself and everything. Can this computer, learn to play these games? Okay. So like if you remember, I hope many of you might remember, because I remember, those old days of Nokia phones, and there used to be these games in those phones, right? So like this is a ping pong game, right? You have to keep the ball always in the environment, right? By sliding these two sliders at two ends, or this breakout game where there is a slider at the bottom. And this was more famous. Like I played this more than the other one. So you have a slider at the bottom and there is a ball, and then you keep the slider and push the ball always upward, and you have to break this whole wall, whatever you had. Right? These are very simple games, right? And there's not a lot of information in these frames, right? However, all these are control tasks. All these are control tasks. Very simple control tasks, you can say toy task, but these are control tasks, right? Can computers learn to solve this control task without any explicit programming specific to the game? See, we as humans, once you start playing this game, we're not asking everybody how to play this game. You keep on playing, suddenly you start improving in the game, and your scores are going up and up and up. Can the same thing happen with a computer, where there is a single algorithm, and that single algorithm tries to learn the best strategy or the best way to play all these different games? Like there are two examples I showed you. So these are part of these Atari arcade games of 1970s and 80s that even came into the initial mobile platforms. And those earlier brick games, if you remember, we used to have some interfaces. We used to play brick games, right? Right. So this was the initial motivation, that how to solve this problem, because because here if you talk of number of states, even in this system number of states are huge. Right? Although these are very simple examples of the game, but number of states are enormous here also. You can't maintain a Q value. Okay. So with this, these people, Amin et al., right? So many people were involved. Like I think there's some 10, 12 researchers that were involved, right? They came up with the first paper, right? And the paper was published in this Neuro Information Processing Systems, right? NIPS, right? It is a flagship conference in artificial intelligence. So in 2013, they came up with this paper called Playing Atari Games with Deep Reinforcement Learning. And this was the initial success story that linked deep learning and reinforcement learning together. Okay. Later on, they improved upon it, and finally, they published a paper in Nature, right, on the same concepts, right? But yeah, they could do it over 50 such games, a single algorithm that is able to beat human records in 50 such games. It was an achievement for computers. Okay, you're not programming a computer program for each 50 different games. There's a single program, and it is able to play all the different kinds of games and beat all human records. So the next paper came in Nature. Again, a very flagship. I hope everybody knows Nature publishing, right? And this paper was human level control through DeepRL. The concepts in both the paper are almost same, and we are going to discuss the model that was proposed. And as you can see, this is pretty recent, 5-6 years only. Okay, so we will discuss this model, and then we will discuss some improvement on this model again in last 3-4 years. Okay, Right. And at the bottom, you can see all these different Atari games. The first two I showed you in videos, right? But then these are all these simpler games like shooting something and Space Invader and those kind of games. Okay, so just now how to play these Atari games for researchers or AI scientists, this was very interesting. Okay, so the first, so if you talk of the kind of problems that puzzled AI scientists a lot, initially it was chess. Okay, so if you see the literature of 70s, 80s, 90s, AI scientists were more focused on how we can create a computer program that can beat a human grandmaster in chess, and that got done in 1999. There was this IBM Deep Blue that could beat the human grandmaster of that time. Right? So the interest then faded. Like, yeah, we achieved that much. What next? Because even beat, so the thinking was if we could beat human in chess, we could create a computer program that can do all the jobs, AI program that can do all the jobs, which is not true because that didn't happen, right? Yeah. So then the next problem came that can this program generalize, right? Can a program learn all different like a single program can learn all different controls, and we struggle for 15-16 years for that. Even after this 2015, in 2016 this Google DeepMind people held a competition for this World Go Championship, right, against this Lee Sedol, who was the grandmaster of this game of Go, and they could beat him, and the computer could beat him. And after that I heard that he stopped playing this game of Go because I know a computer could beat him in the game, right? So there was no fun then. Anyways, right? So we took this much time when this another big, you can say change came in the world of AI and AI algorithms. Let's see when the next change will come. Okay, so we'll move forward with this now. So here, how did they achieve a single algorithm learning or defeating human players in all the different games? Okay, so they established something called a deep Q network. So obviously they created a deep learning model which they nicknamed as deep Q network, which was a deep neural network for Q value function approximation. What we want to do, given any state and the action in that state, we want the model to predict the optimal Q value. Right? And as I told you earlier, optimal Q value means what is the maximum reward I can achieve if I start in that state and execute action, particular action A. Right? So these values are just talking about maximum possible reward. Okay. And if I can find those optimal Q values, I can always find my optimal action, because optimal action is the action which has the maximum Q value. Okay. So yeah, they use deep neural network. We'll discuss the architecture of the network in the coming slides. And then no prior knowledge was used. So no game specific knowledge, no game specific strategy, right? Such things are not used to train this model. They wanted the computer to learn by itself, by playing a lot of games like we human do. Initially, we perform very bad at these games, but as we keep on playing, we keep on developing our mental models, and suddenly, like not suddenly, but after a lot of trial and error, we actually become very good, right? We create mental models, we learn, right? So they wanted to replicate that whole function. And we are not storing Q values, mind you. We are not at all storing Q values for these state and actions in our mind when we are playing, right? So a similar approach where they're also not storing Q values, right? They're putting a network for that. So yeah, so what their algorithm perceive is this RGB matrix. So this frame, as you can see, right? This frame is given as an input, only this frame, and even the color information from this frame was discarded. Okay, so only the frame, the way it looks on the screen, that was given as an input to the algorithm, that this is whatever it is. You think it is a state, action, whatever, this is the thing. So this basically was the state, right? So the RGB matrix of pixels was given, and the change in the score was given as reward. So your score, whatever was the change in score, whenever you apply an action, that was given as reward, right? Because that is the best reward in any game, right? So the reward formulation was very simple, but there is a catch to it. I'll tell you later. Okay, and then What are the actions? Actions are your joystick inputs, right? So those joystick buttons, or if you play with phones or whatever, are the actions possible for each game, right? So if you're playing Mario, there are more actions that are possible. Mario can jump and do other kind of activities. It's only jump and moving forward and backward and all that. But like here, there are only two sliders. These sliders cannot jump, just go up and down. So there are only 2 or 4 buttons that you can use, right? So whatever are the number of actions possible in a particular game, from the joystick input, that is what they considered as set of actions. So in a joystick, typically they considered 16 actions, I guess, right? Or using all the combinations. Color information was discarded, I told you. So they used all these frames, and then in different frames, different games, this frame can have a lot of color information. They discarded all the color information because maybe that it was not adding any value to their learning. Okay. Now this fifth bullet is important. It says a sequence of 4 previous frames is used as a single state. Right? So I told you they give these frames, the RGB frames matrix, as an input. But a sequence of 4 frames was used as a single state. You may ask the question, why? Why not a single frame just used? Okay. It was a sequence of 4 previous frames was used because in all these games there is some motion involved, right? Like in this particular game of ping pong, the motion of the ball is important to know, right? You have to understand the motion of the ball, otherwise how would you move? A single frame does not give you that information, right? But if I give you last 3 frames more, right? So if you give you a stack of 4 consecutive frames, right? And looking at the position of the ball in those 4 consecutive frames, you can definitely make out the motion, right? Motion of the ball or any motion that is happening in these games. And this motion information is important for all these kind of games. For that reason, they used a sequence of, so for every next frame, they use last 3 frames. So always a set of 4 or a window of 4 was used, and all the frames in that window was used as a state, and then you move the window 1 step forward, 1 step forward. Okay. Now the last point, it says the rewards are represented as plus and minus 1, plus minus 1, right? Why so? So that means whenever there was a positive change in the reward that was given inside for the learning was plus 1. Whenever there was a negative change in the reward that was given inside the algorithm was minus 1. Why? Because in different games, the scales of the reward were very different. In one game, the rewards were increasing in hundreds. In another game, the rewards were increasing or decreasing by only in 10 or in plus 1 or minus 1. And this different scale, yeah, and if you're trying to train a single algorithm, right, then they actually create a lot of trouble with this gradient in back propagation of this neural network. Yeah, because the scales are different, right? So if you, then obviously the gradient value will also be high, and accordingly the parameters will get trained. If the reward value is very low, right, and both are positive reward, but the gradient value will also be low, and the update to the parameters will also be low. To get rid of this problem, they said, okay, nothing doing, all the rewards are plus and minus 1. Okay, if there is a positive change in the score, it is plus 1. If there is a negative change in the score, minus 1. Done. So this was the learning setup. Okay, and this is how the model looked like. Okay, again, just a visual representation of the model, right? Not the actual model. The input is a stack of 4 frames. Okay, and then they had I think 3 set of convolution layers. Not all sets are shown here. Okay, so they had 3 set of their CNN layers. Okay, and after these 3 set of CNN layers, they have 1 fully connected layer, 1 2 fully connected layer. Okay, and finally all the action outputs. Okay, so these all action outputs tells you what is the Q value of that action. Okay, so more detail about the architecture I have in this slide, right? The same thing that I have explained you earlier. Okay, so stack of 4 frames, and then you have CNN layers, and then you have fully connected layers, and the final output of fully connected layer are these 18 or I think 18 joystick positions as the output. Okay, this is the model architecture that they came up with. Now the important question is, if you ever work with deep learning, the most important question comes out to be, what is the loss function? right? Without a loss function, how do you train? How do you calculate your error and gradient and propagation? Everything is dependent on the loss function, right? And loss function makes a lot of difference in learning, right? And as I told you earlier, in any machine learning, we learn on errors. Here also we have to learn on error. Now the question is, okay, ping on your Google chat screen if you get the answer. Okay, so I'll not wait for somebody to answer. Okay, the question is, we don't have the ground truth values in or the label data in reinforcement learning. We don't know which action is the best, or we actually don't know what is the best Q values of all the state. We don't know the Q values, right? And obviously these are so complicated system that we cannot employ any other algorithm to learn the Q values and then we can train these models. Not possible, right? So if we don't know the ground truth, how do you calculate the loss function here? And then, because without the loss function, you won't be able to train this network, right? So we have to think about it. What would be the loss function here? Okay. So yeah, if you get the answer, ping. Otherwise, anyway, I have the answer in the coming slides, right? Let's see what I have next. Okay. So while you're thinking about the answer, I'll explain you something else. But yeah, I'll tell you the answer later. So one thing is this loss function that we'll discuss anyway. They figured out the loss function, they put the loss function there, okay? But they ran into some very specific issues with training of this DQN model, right? Now, what was the issues? First thing is naive Q learning in a typical Q learning setting, okay? If you try to train it as you train your Q learning model, okay, then naive Q learning oscillates or diverges with neural network. Right. So if you try to replace, like you keep everything same as in Q learning, same equations and everything, right, and use the same update equation to update your Q learning model, right? The issue was the network was oscillating or diverging. It was not converging. So it was not actually learning something. It was just learning was going on, and no final output. The training loss was not going down. It was sometimes goes down, goes up, goes down, goes up. And they figured out the issue is because the data is sequential and successive samples are correlated. What is the meaning of this? Again, this is a very important assumption that we usually forget, but it is always there whenever you are training any supervised learning approach. We always assume that the data that we have to train any supervised learning model is IID data. Rings some bell? I hope it rings, right? IID data, right? Identical and independently distributed. Independently distributed. So if the data is very correlated, the data that you're using to train any of these deep learning model or supervised learning model are correlated, then learning won't be good, right? Or maybe the learning may not converge. But in reinforcement learning, that is always the issue, because every next data point is actually dependent on the previous data point, because from the previous state you choose an action and you generate next state and next action, and then from there you again choose an action. So all the three data points are somehow correlated, right? That became an issue. Okay, so that was first problem. Second was policy change rapidly with slight change to Q values. Now, what is the meaning of that? See, we say we extract, how do we extract policy? So we said that whichever Q value is maximum, right, that action we will choose as part of policy, right? Whichever has maximum Q value, that is our policy. Okay. Now this max function, whenever we do a max over a set of numbers, right, it will always choose a maximum definitely, right? But even if the numbers change by a difference of 0.00000001, right, up to some 10th decimal place, also if there is some change in the point values, then also the max will flip, right? So what they're trying to say is, no, when you're trying to learn this kind of a complicated model, right, the output Q values will obviously change in every iteration by a bit. Some decimal point change will happen. Even for that decimal point change, the policy was changing because the action will because the max is changing now because of those decimal point. So the agent will always choose the max action. So it will be a different action this time. And this started making the policy oscillate. So even after a lot of training, whenever you're giving a state in an input, because of so many values and everything, obviously there will be some change in the output Q value, some minute decimal level change. But because we do a max function, the output action was always changing, right? And this created an issue because your policy is not stable. Every time the policy changes, how do you find the optimal policy? Because your next data is also dependent on the policy, right? And so because the data is also dependent on the policy, your distribution data can again swing from one extreme to another extreme, because one action says go left, another action says go right, and the Q value difference is very minimal, or not the actual difference is coming. Okay, so this was the second problem. And the third problem they had is with the scale of reward in Q values, because there are different games that they're trying to train on, right? So the scale of Q values and the scale of reward matters a lot, right? That defines that your Q values will be in thousands, or the Q values will be a number between 1 to 10, or maybe a number between 0 to 1. Right? That is scale of Q values, and scale of rewards is more or less game dependent, right? So and that this scale makes the gradient unstable when you do backpropagation. So these were three major stability issues that came into creation of this DQN network. Okay. Whatever solution they provided, that has become a norm in these deep learning models, deep reinforcement learning model. Whatever solution to these problems have been provided, right, by them, that has now become like the standards. So anytime you implement any deep reinforcement learning, these problems are already thought of, and whatever the solutions available, now you automatically fix those solutions. Okay, or the way you implement deep reinforcement learning is always using such an architecture. Okay, then you play with your loss function, you play with some parameters around loss function to maybe perform better. That is what now researchers have started doing. But yeah, this was the the seminal change, right, or the seminal work, you can say. So what are the solutions, right? First problem was NAQ learning was not working. Right? First problem was NAQ learning was not working. Why? Obviously, data was very much correlated. And second thing is, another problem that they had is with this loss function. Okay, it turns out even the loss function was not stable in the typical Q learning. Like if you use Q learning equations, right, then the TD error that you calculate in Q learning, right, that could act as loss function, you may think, right? But that TD error, right, was a biased TD error, means the target of that error is also dependent on the Q values that you're trying to learn. So you're calculating the error, right, from some target where the target itself depends on the learning model. So then it becomes like a chase, right? And so you're trying to achieve a target, but by the time you reach to the target moves, right? Because we don't know the ground truth. Okay. So in order to solve these stability issues, first thing they did is they created two separate deep neural networks. So whatever deep learning architecture I showed you, they created two copies of that network. Same input, same output, two copies. Okay. The first copy, the main copy, they call it Q network, which is their learning network, which they are trying to train and learn. Second copy, they call it a target network. Okay. Another network, they call it a target network. And in this target network, they froze the parameters of the target network. So that means they're not updating the parameters of a target network with every iteration. They froze it, they fixed it. Okay, so all the weights or the parameters of the target network are fixed, right? Where the parameters of the Q network keeps on changing. Okay. Then they use something called experience replace. I'll tell you more about it. But this experience replace was used to break this successive or correlation among the samples that you are collecting from the environment by executing actions and state and everything. So this consecutive sequence of this samples that you're receiving, to break that correlation among the samples, they use something called experience replay. We'll discuss that. And obviously the third problem that we had with the scale, they clip the rewards to the sensible range of +1 and -1. Okay, so the last one is easy. Now we have to understand what is this Q network, the target Q network, or target network, and how it helped in learning, and what is this experience replay. These are two things that we should now understand. Third one is easy. Right? So two separate networks, right? Why two separate network? Because first thing, we don't know the ground truth, right? So what they said is, okay, since we don't know the ground truth, let us use the TD error. But in that TD error, I'll show you the equation in the next slide. In the TD error, right, whatever is the target, right, that target Q value will come from the target network, and whatever is the current Q value of the state will come from our learning network. This way, they fixed the target. So instead of a bouncing target that always moves whenever you update the parameters of your Q network, the target become fixed. So now your network can learn at least to reach to this fixed target. Okay. However, they did not keep the target always fixed, because initially when you're initializing the networks, it's all random parameter values, right? So what did they do is they train the learning network for some time, and after some 1,000 iteration or 10,000 iteration, they copy all the parameters from the learning network to the target network, and again keep it fixed. Okay. So there were periodic updates, not every iteration updates to the target network. Okay, so that you can improve upon the target also, right? Okay, yeah. So this is the fixed target network. You can see, if you see this, what is in this braces with a square here, right? This first part is actually the target. It is the same thing that we had in our Q learning equation. We had an alpha multiplied to this whole thing. It's the same thing. The problem was this Q function is dependent on this theta parameters, right? So if this Q function is also coming from the same network that I'm trying to learn, the Q function will change always whenever I update my parameters, right? So target was not fixed. So then they created this Q target network, and that's why it's shown with this theta minus. So theta minus represents a fixed copy of the same network, but parameters are fixed. Okay. So the Q values are derived from there, and these became the Q learning target. And this Q is my current Q value, whichever my model is currently predicting. Right? We took the difference of it, and they learned on the MSE error on this particular difference. So this was the cost function. This is how they designed the cost function to train their this DQN network. Okay. Second is this idea of experience replay. So what they said is that, because all the consecutive samples are correlated, okay, let's not use consecutive samples to train our DQN network. Instead, whenever you collect a sample from the environment, this is how a sample would look like, right? State, then you took an action in that state, you'll get some reward, and you will know your next state, right? This is one sample. Let us store this sample in some kind of a memory, in some kind of a buffer. Okay, so we always execute action, or whatever the model says that this is the best action in this state. We take that action, we execute it, we get a sample. We don't use that sample to directly update our parameter as we used to do in Q learning. Right? Instead, we store that sample into a buffer. Okay. Now what we do from that buffer, here it is called the replay memory. Okay. And that's why it is called experience replay. So these are the experience. These transitions is one sample of experience, right? You're replaying the experiences. Okay. So here, these experiences which are stored in a memory, they sample a random mini batch. So again, now you are sampling a random mini batch so that the successive samples are not correlated at all. Initially, there might be a lot of correlation when you're booting up the learning process, right? But after some initial burn-in period, it will stabilize. Okay. So we sample this mini batch of these experiences or transitions from our memory buffer, and then we use this mini batch to train the network with the same error that I showed you earlier. right? So all the error is calculated on this mini batch, and then one iteration of training is performed. Okay, and hence you have your DQN algorithm. Now this may look very complicated to you, that so much of the pseudocode is written, but I will take you through each line and you will find that it is actually very easy. Okay, so let us start. We are initializing something called a display memory buffer. Some memory buffer is initialized. Okay, initialize means a memory buffer, an array is kept, right? Then we are initializing the Q values, a Q value function with random weights. So this is basically saying you're putting some random arbitrary initialization of your Q network, right? So all the network parameters are initialized randomly. And with the same parameter values, you updated your target network. So target network is not separately initialized. Only one network is initialized. The other network copies the parameter. Okay. Then we are running the system for some M episodes. So because these are games, right? So whenever you start a game, you'll finish the game, right? So whenever you're starting anything in the game, there will be one terminal state, and then you have to start again, right? So for training, we always play the game M times to train the network. This M is quite large. This M is in millions. It's not some 10 or 100 episodes you're talking here. Okay. Sorry. Then what we do? Then we initialize our, let's say, the initial state. So the phi1 simply represents a combination of some last four frames to create our initial state of the system. Okay, that is where you initialized. Then from time 1 to t simply represents the length of an episode. Okay, so for each time step of an episode, if we know the length, let's say some length of the episode, we select some random action with some probability, because initially we don't know which action is best. Okay, we select some random action with probability epsilon, or we select a greedy action based on our Q values. This process is called epsilon greedy approach. Okay, which is one of the ways how you choose your actions while learning these algorithms, right? So we choose an action. That is the thing. This 2 lines simply says you choose an action. Then we execute the action in the emulator of the game. So obviously we send the action to the emulator, the action gets executed, and what we observe is the reward, which is now +1 and -1, and the next image. And next frame will come, right? We take that whole information, right? And we set our next state using this image xt +1, right? And after all the pre-processing, so this phi simply represents the stack of frames with all this information into it, which creates the next state. So here the states are, because it is the combination of 4 frames and everything, it is shown using phi. Because we executed one action, now this creates our one sample, which is phi t, at, rt, phi t +1. Current state, action on the state, reward, next state. Right? So we store this whole transition into our replay buffer. Then we'll sample a mini batch from the replay buffer. Right? If we have reached the end of the episode, then there will not be any next state, because it is the end of the episode. So we will only get the reward. Okay. If it is not the end of the episode, then we can create our target as reward plus gamma times max of the Q value from the fixed target network. Okay. So this is how we calculate this yj, which is the target variable, and then we perform gradient descent using y minus current Q value square, like the MSE error with respect to the theta parameter. So this perform gradient descent point actually is talking about running your backpropagation using this error, and then the whole thing repeats. So if you read, it's actually very simple, right? Let's see how much of training then happened to train this complicated network. Again, this was the first one, right? Many better performing networks have been proposed since then. Okay, so they trained on 49 Atari games, 49 different Atari games. You may think, why 49? Odd number, right? Like they should have trained on 50. Why 49? So my guess is they must have tried on 50, but they got results only in 49. So they said 49. It's my guess. Okay. Later on, anyway, they improved beyond 50 also, with 55, 60 games and all that. They used RMS prop algorithm. So that is the used in the backpropagation. RMS prop was used. They used 50 million frames. So individual frames of games, right? 50 million frames were used. 5 crore frames were used. So yes, training such networks is no joke. Okay, you cannot just train it. Okay. Training time was 38 days. Almost 1.5 months, they were running their servers on these many frames. Right? So they really wanted to squeeze the system and get the training done. Imagine their electricity bills running their big servers for continuously for 38 days. Okay, and the replay memory buffer that they used, it could store only 1 million recent frames. Okay, and obviously 4 frames, or every 4th frame the action was performed, right? So they always used this stack of 4 frames. So this was their training setup, and as you can see, it was a very complicated training. Like imagine that one of the parameters was not properly set. The training time is 40 days. So after 40 days, they will realize, oh my God, one parameter was not set. And then they will set and again run for 40 days. So 3 months just to get one good result. So obviously a lot of care has to be taken, and they must have taken. And yeah, DKN was the initial success, right? So obviously they must have had a lot of such hurdles. Then how do you evaluate these models? So, one policy came, and the policy says it is good at playing games and playing multiple games. How do you evaluate that? Because for all these games, you cannot bring in a human grandmaster who can play well and then make them compete with each other. You have to have a good statistical method to compare, right? Good metric. So they designed a metric. They said, agent plays each game 30 times for 5 minutes with random initial condition. So you start the game from any point, and this trained agent, the agent that we have trained now, it will play the game 30 times, like 30 episodes from the game from the same start position for 5 minutes. Okay. A human will also play the same game in the similar scenario. A human who is good at playing those games. Okay, and you're recording these statistics. Then a random agent again plays. A random agent means an agent that takes random actions. Agent with a random policy also plays the game, right, in the same scenario. And this random agent is going to be our baseline. So they are going to see how better a human perform as against a random agent, or how better a human can score as against a random agent, which is our common baseline, and how well the trained agent performed against the common baseline. And this were the results. Okay. In gray, you have the best linear learner, like a human. And then the blue one is your DQN. Right? So like here, DQN performed 2,539% time better than the random agent, while the linear learner could only perform 336% time better. Okay, so these are the games, as you can see here towards the left, are the games where the model performed either at the human level or above the human level, much better than the human level in all these different kinds of Atari games. However, there were other games where it could not do so, where it could not beat human level understanding of the game, because maybe that game required more knowledge development. Right? It required more than what this in other games where we could achieve. And obviously, then as I told you, there have been now methods which you again improved on these remaining games as well. Okay. So yeah, this was the DQN model. Okay. And then now in just half an hour that we have left, we're going to discuss the improvements that has happened over DQN model. So the initial first improvement is called double Q learning, or this double DQ network. The paper actually was published in 2016 in AAAI. Again, one of the very flagship conference in AI. What they said is, they said that the way you are using this update equation or this loss function calculation is actually again creating some kind of bias because of this choosing always the max value over the same Q value coming from a fixed network. Okay, so they said, okay, let us change this equation a bit. Again, the same thing that we do right now. This is like change the cost function. So they are changing the cost function to see if there is an improvement Obviously, there is some logic behind changing the cost function. It's not like out of the blue they came and just did some random thing. Okay, so the logic is this double Q learning method that came into 2010, which actually said that in typical Q learning method, our base Q learning method, there is a bias called maximization bias that creeps in because of that max function, this max function here. Right? This actually induces a maximization bias into the system, and because of that, the learning suffers. So they changed the way these update equations were managed or were written. Okay, where they said that instead of one queue, let us try to learn both the queue networks. So two queue networks, and learning is happening for both. Same idea was applied here. So here they said that instead of only learning one set of parameters in Q learning, why not alter that? And since we have two Q networks, so let us alternate those network parameters in order to get this what you call target value, only the target value. Okay, this will remain the same, only the target value we're talking. So the way they changed it, they removed this max function from here, right? And they put it inside. To choose an action, the max function is only used to choose this action A dash. And for that particular action, the Q value was chosen from theta minus parameter. So this was the change. You see, the R remains the same. It will be the same reward. Gamma remains the same. Now you're directly using the Q value from the fixed network, but the state, and then the state is also the same, whatever is your next state, right? But the action for which the Q value is chosen is taken from your learning network. The action is taken from the learning network. Okay, so this was the change, and this was the result of the change. Right now, they could actually learn on 57 Atari games from 49, and they had improved results on 57 Atari games. And since there was already a DQN model, so they directly compared with the output of the DQN model. So as compared to DQN model, this model, the double DQN model, could now perform better in at least 57 games, 57 Atari games, right? 6 more than what could be achieved. And even whatever was achieved earlier, the DQN model can even score much, much higher. So the maximum score that we saw there was somewhere like 2000%. Here, it went up to 7500% gain over a random agent. Right, so you can see even the performance went up, and even more games was included. And the games that got included are here highlighted in this, bold font. These are the 5-6 extra games that were added. Right. So this was first improvement. People are not just kept there, and they started looking into that how we can improve even further. So one big problem that you can still see is the training time is very high. 40 days, too much. Who is going to wait 40 days? Every time you're training for a game. So if you're training for these kind of games and you're taking 40 days, if you have to train for a real world task, you will take years, at least a year, right? So then people started thinking, how can we reduce the training time, right? How can we improve upon it even further? And then they looked into this replay buffer. Okay, so they said that in this replay buffer, the way you are randomly choosing these experiences, they sample a random mini batch of experiences to train the network. They said, why are you choosing randomly? Why not choose those experiences which has more value for the learning? Right? And let's not choose those experiences which are adding very less value to the learning. Then the question is, which experiences add more value and which experiences add lesser value, right? So, well, the answer to that question was in this equation. If this difference is high, then the parameters will get updated more. If this difference is very low, but what is the aim here? The aim is to make this difference 0, right? Because this is error. That's the cost. And the aim is always to make the cost 0. So if you have experience which are automatically giving you the values of this difference as very close to 0, then those experiences are not going to add a lot of value to your learning. Instead, if you have other experiences, those transitions where the error is still coming out to be very high, then those are more valuable, right? So this concept they used, and they devised something called prioritized experience replay. Let us set some priority over how you're choosing these transitions from that replay buffer instead of doing a uniform sampling, right? How to set those priorities? So priorities are set using, again, what was the error with each transition? What was the DQN error with each transition? Okay, so these DQN errors were recorded, right? And then they created this probability function, which distributes the probability of selection over your replay buffer. Now you are choosing, you will choose your transition. So you may choose the same transition even more than once also based on this priority value, or based on this probability value. The probability value are derived based on the priority. Okay. And then they came up with two variant that, how do you define this priority, right? One could be directly defined based on the error, right? The delta I error. This is the delta I error, DQN error. Another could be based on the rank, right? So if you like sort all the transition based on the DQN error, then you decide the priority based on this one by rank of I. It is an indirect relation with the, it has a relation, right? But it's an indirect relation with the DQN error. So this is how they define the priority. And then using that priority, they came up with this distribution function, which distributes the probability values. And then they said, now we will use the same DQN network, but we'll choose the transitions this way. And this is called prioritized experience replay, PER, another better method. It appeared in ICLR 2016. Okay. So this was the model. I'm not going to explain you this model, the double DQN with this prioritized replay. The only change that is happening from the previous model is this sample transition, where they're calculating a priority value. Okay. Once based on this, and then they calculate a weight value for this, because you're changing the distribution, so you have to account for this distribution. So they calculate some important sampling weight for that, and then this weight and whatever transition you have chosen, those were used to update the parameters, and rest remains the same. Okay, so there are only 2-3 lines here that got changed in the original DQN paper. The rest, everything remained the same. Okay. Right. So let's skip this important sampling weight, right? So this was done in order to, because, once we set a priority, we are changing the distribution, how the data was getting generated. And the change in distribution is, again, can affect our learning, right? Because our learning is based on how we are experiencing the environment. But by putting this priority, you're changing the way the agent has to experience the environment. So you have to counter that. To counter that, they came up with this called important sampling weight, which they added to each of these updates that they were doing, right? So that the correct policy is always learned. Okay. Right. And then this is their result, right? Again, they performed on these 57 games, right, which used double DQN and prioritized replay, both, right? And then they showed that how this rank based and the proportional priority, it compares with the tip. So the comparison here is with the typical double DQN store, what we have seen already, right? They compare directly only with the score of double DQN, not with any random player or anything. Okay, so this is the gain above double DQN. So there's a 200% gain above double DQN. Okay, so even it became much better for many games. Okay. Right. So in all these 2-3 methods after DQN that I've discussed with you, see, the architecture remained the same, right? The basic architecture, they kept the same, right? And the only thing that they were changing is maybe the way you're choosing your transition, or the way you are updating or writing that loss function. Right? Then came this paper, which is called Dwelling DQN paper, right? Dwelling Network Architecture for Deep Reinforcement Learning in ICML 2016. I hope you must be aware this ICML, International Conference on Machine Learning, is again one of the flagship conferences in machine learning. And this was the best paper in that one, where they changed the architecture of this whole training model or deep model. They said, no, let us come up with a different architecture. Okay, and then with this different architecture, can we further improve on the kind of learning that we're doing, or the learning performance if it can improve. Okay. Now, what was the concept here? Okay, so here they use something called advantage function. I'll tell you what is the advantage function. Okay, but the idea was, they said, look at this game. So this game that is there on the right side of the screen, as you can see, right? This is a car game where there is a car and there is a road, and that job of the car is to be on the road and move forward. Okay, they said that, I don't have to find the value of all the state or all the positions on the road. Okay, if there is nothing on the road, like in this situation when there is nothing in the front on the side, maybe I just have to find the value of going in the forward direction, and nothing else matters. So as long as I find the value of that, what is the value of being on the road and going forward, it is enough. Okay, so that is where this orange thing is shown, which just says that, here the most important aspect is to go forward and just know that what is the value of going forward. If you see the snapshots at the bottom right, okay, now what happens is, along with the car, right, there are other cars in the environment on the same road, right? And the game name is this Enduro, right? And since there are other cars in the environment, now it becomes important, right, to know that what would happen if I take a left turn, or little bit of left turn, or little bit of right turn, because I may collide, right? So I don't have to learn about the value of all the actions every time, right? I can learn the value of all the action only in these situations where those actions are important. Otherwise, I will just learn the value of going forward. Right, and this is how they describe that, we need a different architecture, because learning the value of all the actions is not always important, which they were doing earlier in these kind of games also. And that's why they had a lot of more values to learn, and not all values that they are learning are always useful. Right, and this is the idea. So the idea was, features needed to accurately represent value of states. Features that are needed to accurately represent the value of state may be different from those needed to specify the difference in action. So till now in the Deacon model, you're just taking a state and using all the features of the state. What they're saying is, maybe not all the features are always important to specify the value function. Right? So they use this particular thing called advantage function, which is nothing but the difference of your Q function and the value function. Q function is the value of a state, and value function, state and action, and the value function is simply the value of the state. The difference between these two is your advantage function. What happens is, if you learn the optimal policy, right, at optimality, the Q value and the value of the state becomes similar, or same. Not similar, same. Since they become same, the advantage function becomes 0. So if you have a non-zero advantage function, that simply says you have not learned the optimal policy yet. Okay. If your advantage function becomes 0, right, that means whatever policy you have learned is actually becoming optimal policy. So they started focusing on this advantage function instead of learning Q value function, because it was simpler, right? Whatever advantage function you're calculating, just try to make it 0. Right? And then this was the change in the model. Okay. So this was the typical Deacon model. You had a lot of CNN layers, of fully connected layers, and finally all the Q values. Right? Here also, because you want to learn a policy, you always extract the policy using max Q value. So you need that as a final output. But they changed the architecture. They bifurcated the architecture after this last fully connected layer, when they said that, yeah, we'll use one strand to learn the value function of all the state or the current state. Okay. And the other one we will use to learn the advantage function. And ideally, advantage function should be 0. Ideally. right? So whatever is the advantage function predicted for the current policy, right? Because maybe the current policy is not optimal. If it is not optimal, advantage function won't be 0, right? So then, and you can always combine the value and the advantage function to get your Q function from the same equation. I put this value function here, you sum it up, you'll get the Q value. This is their idea. Okay. Now, whenever you propose such a network, there are obviously some specific things with the network that you have to take care of, special cases of the network, right? Their problem was, this uniqueness of advantage function. It turns out because advantage function is this difference, right? And let's say the difference is 2. There are a lot of, and you're learning the value function. Let's say you're fixing the Q value learning. You're also learning the Q value and the value function, right? And that if the difference is 2, there may be n number of combinations of Q and value function available that can result you the same advantage function, right? Because the difference of the 2 is also between 10 and 8, and the difference of 2 is also between maybe 6 and 4, right? So the uniqueness of the advantage function and this value function became a trouble for them. Okay, because rest remain the same. They also said, let's use CNN network. We will create a network with the advantage function. We'll put the parameter as alpha. We'll create another network for the value function. We'll put the parameter beta. And now you have your Q function, which is theta, alpha, and beta parameter, right? Where the value function and advantage function is simply summed up. But since we have to learn these parameters, the trouble came because if the parameters are not unique for value function and advantage function, like a lot of parameter setting can result in the same Q value, then how do you learn? Right? So to establish that, the uniqueness of your this Q value function, right? They change the equation a bit so that the uniqueness can be ensured. So they achieved it using one of these two methods. Usually they use the first method, right? The first one says that let us force the Q value to become equal to value of the state, right? And this is the condition for optimality. That's the condition for optimality. How do you force it? Well, you subtract the average or the maximum advantage function from your current advantage function. The maximum advantage is equal to the current advantage, then it becomes 0, the advantage becomes 0, and that is your optimal action. Okay. So this was one of the method, but there was some non-linearity here, right? This is a non-linear function, this max function. And we tend to reduce non-linearity because that complicates the matter. So the second one they used is, let us subtract the mean of the advantage function from our whatever advantage function we are predicting. Okay, this was more stable, they found. Okay, and that is how they ensured the uniqueness of these Q values. And then then they trained it, right? And they trained and they compared with the DDQN with PER model, whatever is the previous model. What they showed is how their model even improved, even for some gain 1000% with this DDQN model, which is already an improvement, like DDQN PR, which is an improvement on DDQN, which is an improvement on DQN. Total improvement was, you can see, some 9000% or so. For that particular game, obviously, multiple games they took. Okay. So that particular extensions that these model added, the dueling network model added, was obviously they had prioritization, they had a dueling network, and they also did gradient clipping. Okay, so they used batch normalization and all the tricks of training a deep learning. So creating this network is one thing, but training them is a hell of a challenge. It's not easy, right? You have to work with them a lot, and you have to come up with these kind of insights to make them work. Now, obviously, so many of such improvements were happening since 2015 when the first model came. All these big researchers working in the domain of RL and AI, they were proposing new methods that we are able to achieve even more. So this group of Hazel et al. In 2018, what they said is, let us put everything together and let us see what happens. So they created a deep reinforcement learning model called the Rainbow model. Okay. And this Rainbow model had all the best elements of all the models that came. So you had DQN, DDQN, prioritized DDQN, dueling DDQN. Then there's a model called A3C and all that. Okay, they put all the benefits of all the model together in a single model, and then they said that, yeah, let us see that how this one compares, right? So as you can see, the paper's name was combining improvements in DeepRL. Let us combine all possible improvements, and then they showed us the final model actually performs much better, this rainbow model, than all the earlier proposals. And this initial DQN model, right? As you can see, it is actually at the bottom, the initial DQN model. Right? So a lot of improvements have been done, but there is an issue. Right? If such improvements have been done, then why don't we see robots moving and cleaning our dishes? With so many improvements, all these improvements now, they became too much focused on these Atari games. So somewhere, it's my feeling, don't quote me on this, but maybe a little bit of overfitting also started happening. Overfitting on these arcade games, these Atari games. Obviously, the models has a lot of insights, and they can actually be now applied in other domains, and they have been applied in different kinds of applications in various domains, in computer networks, in robotic control tasks, right, in recommendation systems. In a lot of places, these models have been applied, and the results are good. In UAV navigation and all, also people are applying. Okay. But maybe this rainbow model you may not be able to apply, because maybe all those improvements are not required for your domain, right? So yeah, those are like, you have to take it with a pinch of salt. That okay, so much improvement is okay, but maybe the final rainbow model is not that popular. The DQN model is actually more popular. Okay. Yeah. So with this, now I'll just give you a very quick snapshot of this superhuman performance of these DeepRL method in 2016 on this podium, where this is Lee Sedol, and he was playing against the computer, and the computer's name was AlphaGo, right? And he was Korean, so AlphaGo became very famous in Korea, and people suddenly, the whole nation knew about AI, and what AI can achieve. So this happened in 2016, right? And a lot of interest then came into these deep reinforcement learning models. So we will quickly go through, we'll not go through into the algorithm. The algorithms are very complex, okay? But we'll try to at least understand very top level details of this model, okay? So what is the game of Go? So what you see in the screen is the game of Go. You have a board, and you have two kinds of stones. One is a white stone, and another is a black stone. The game is to collect as many stones as possible. Okay, so you have to collect as many stones as possible of the opponent. Okay, so the more stones you collect of the opponent, the more. And the game is to put the stones on this particular grid. Okay, so you have to reduce your own set of stones and collect more and more stones of your opponent. And as you can imagine, I don't remember all the rules of the game, but as you can imagine, you will be able to collect opponent's stone once you encircle all the stones using your own stones, right? So whenever you encircle, like you create a boundary around the opponent's stone with your own stone, you grab all those and you take it out of the board. The thing is, the state space in this game, this simple board game with very simple rule, is huge. State space is in the order of 10 raised to power 140. Imagine number of zeros after 1, 140 zeros after 1. That is the number of states in the system. It's huge, right? And that's why this game was was a challenge for AI researchers, and they wanted to solve this, right? So I have this video. So the thing is, in 2016, this game came, which the algorithm came, which was AlphaGo. But AlphaGo used a lot of data and a lot of training time, right? Because that was the first version. But then, yeah, these researchers, they kept on looking, and then they came up with something called AlphaGo Zero, which used very lot less data, and the training was also very fast. So they have this very nice infographic that I took from their website of DeepMind, which shows the progression of or the evolution of these AlphaGo algorithms. Okay, I'll just play it for you. So they started training AlphaGo Zero with no prior knowledge of the game, on only the basic rules as an input. In 3 days, this AlphaGo Zero surpassed the abilities of AlphaGo Lee that beat the least at all, right? In 3 days. After 21 days of training, it reached to a level of AlphaGo master, right? That defeated 60 top professionals in 2017. And after 40 days of training, AlphaGo Zero surpasses all versions of other AlphaGo variants that has come up, like the best possible player. So now nobody will have any interest in playing the game of Go because there is a computer and it is established that no human can beat this computer on this game. So this is just a progression. Like after 40 days of training of this new algorithm AlphaGo Zero, it surpassed everything in that particular game. And what you see on this y-axis is called ELO rating. ELO rating is rating specific to players in this particular game of Go. Okay, so higher the ELO rating, you are the grandmasters. Okay. Now, at the core of this AlphaGo and AlphaGo Zero, they use something called a Monte Carlo tree search method. See, in this game, whenever you play a game or you write a program to play the game, you always have to create something called a game tree. What is the game tree? Well, in the game tree at the top, you have your current state, maybe the way your current state looks like, your current pieces in a game of chess, maybe how your pieces are spread. And then you, from that state, that is the root node, you start creating your game tree, means, okay, what action I can take. So if I take this action, then what happens? Then in that state, if I take this action, so, one whole trajectory of strategy, then if you take another action, so similarly, you can create the whole game tree. But in these games where the number of states are 10 to the 140, right, you cannot possibly create the whole. So this game tree was used in chess in 1999, right? They created the whole massive monolithic game tree. And then from that game tree, they knew that what is the best possible action in that state, and then they did it. But this was not possible in this game because the tree would be very deep and you don't have that much time, right? You have to make your decision within seconds. So they used again a tree approach. This is Monte Carlo tree, where they said, okay, we will expand the tree only up to a limit which is permitted in the current time. And after the limit, okay, we'll run what's called a rollout policy, a very simple policy with very simple heuristics method, like some tricks of the game, right? May not be good tricks, but some tricks how to play the game, okay? Which will be very fast. So you can go to the end of the game very quickly with these policies, okay? And this kind of simulation of rollout policies are performed multiple times, okay? And finally, you will get a value of this bottom state. Value means, yeah, in all this simulation, how many times you won, how many times you lost, right? And what is the reward for winning, what is the reward for drawing and for losing. And then that value can be now backed up. And using these values, now you make a decision that what is your next step in the game. Again, this is a very high level overview of Monte Carlo tree search. If you're interested, obviously, you can go and read it in more detail. Okay. So they use this method, right? And this was the AlphaGo Zero self-play architecture. Self-play is another important thing. So these AlphaGo Zero, they train by making the computer algorithm to play again itself. So it was not playing against some players and trying to learn. Every game it was playing against itself only, and by the self-play, it kept on learning. So that is another improvement, that now the algorithms can self-play and learn instead of collecting data or episodes from the net of other plays of the game. Okay. So in the architecture, the current state was given as an input. You had a set of these CNN layers. Okay, and the final output was a probability vector, right, which gave you the probability of choosing an action, right? And then you use this probability to run your MCTS search, the Monte Carlo tree search, right, using these probability values, and then you complete the tree in the available time, right? And then whatever is the value you receive from the tree, accordingly you take your action. And the same thing repeats again and again. Okay. And the output of this whole network is also the final value V, which is like from the current state, right? What is the probability of taking each action? And then what is the chance of winning or losing? Okay. And then the episodes were performed, and obviously then we compared that we actually lost a one, and that difference was taken, and the difference of probability was also taken, and this network was trained in this manner. So I know this is a very high level discussion and nothing is very much clear. I can get it. But yeah, I just wanted to give you a feeling, right? An idea that, what went on to, make such complicated solutions. Okay. So this is their network architecture, right? They used the input of this 19 cross 19 cross 17 image stack, right, with 17 binary feature planes. Okay, so there were 17 of these image stacks, not 4, 17 here. Output was a vector of p probabilities for each possible stone placement, and a scalar v estimating the probability of win, right? And they trained on only 4.9 million games. This is much, much, much less than the initial DQ training that I showed, right? And even their batch size was only 700,000. Again, very less, right? So they solved this very complicated game even with much less of training than what was required with DQN. Okay. Right, so I have almost reached and on time. That is very good. So I've reached this end of this session, and these are the references. So this first book, Reinforcement Learning by Sutton, and Bartow, is like the textbook for reinforcement learning if you want to start reading about this, or start understanding about different reinforcement learning method. So that will be a go-to book, right? I think the first edition is also freely available on the internet, right? So you can have a look. And if you really want to start with reinforcement learning, this will be the book to start. Okay. And all the papers that I've discussed in this session, I have listed all of them here, right? So you can note it down. And if you're interested in want to know more about these algorithms, definitely you can refer these papers, right? So with this, thank you. Thank you for being a nice audience. And if you have any questions, I will be happy to take them.